have these two compounds, and we're going to predict what we're going to get as a product, and we're going to determine, and then we're going to balance the equation. Then we're going to determine whether something is soluble or not, and then we'll do the full molecular, full ionic, and net ionic equation. So that's what we're doing. So when we're doing this, we have to swap the metals. Or you can actually swap the anions. It doesn't really matter which one you swap, but you're going to swap. And so we're going to swap, but we have to be very careful. We're not going to put it up as in the equation just yet. We're going to say calcium, which is a 2 plus, is going to swap in for the aluminum, and we're going to have the nitrate, and the aluminum, which is a 3 plus, is going to swap in with the sulfur, which is a 2 minus. And of course, if we put these together, we're going to have to swap the charges. And now this becomes calcium NO3 with the 2, because the 2 came down from the calcium. And the same thing is going to happen over here. The 2 is going to swap down onto the aluminum, and a 3 is going to swap down onto the sulfide. So now we have the correct charge balanced products. And so we'll go ahead and put those, carefully copying it down, in as the products. Okay, now at this point the equation is not balanced, and so we do need to balance the equation. And so we look over here and we see calcium. We have 1 calcium on each side. Well, so far we're so good. I see 3 nitrates over here on the left hand side with the aluminum nitrate, and I see 2 on the right hand side. Now what we're going to have to do is, since they differ from even and odd, is that we're going to have to put a 2 in front of here and put a 3 in front of here. That way we end up with 6 nitrates on both sides. Okay, and if we do that, well, now we have 3 calciums on the right hand side. We'll have to put a 3 over here to get our 3 calciums, and that should be balanced. But we should always check and make sure that the equation is balanced. So I look over here on the left hand side with the calcium sulfide. I see I have 3 calciums. On the right hand side I see 3 calciums. I see 3 sulfurs on the left hand side, and over in the aluminum sulfide there's 3 sulfurs. And I see I have 2 aluminums on the left, I have 2 aluminums on the right, and I have 2 times 3 in the parentheses on the left hand side with the aluminum nitrate. That gives me 6 nitrates, and I have 3 times 2 in the parentheses for the nitrate, and that gives me 6 nitrates on both sides. So now this equation is balanced. Okay, so when we have the balanced equation, we call that the molecular equation. There it is. And we also have to, our next skill, because there's a couple of skills here. I mean, one, you have to be able to predict the products, and then you have to determine the solubilities so that you can do the full ionic next. Now let's go through and see what's aqueous and see what's solid, and so, or insoluble. And so we look at the calcium sulfide, and we look at our table of solubility guidelines, and we see that sulfides are insoluble except if it has calcium. Calcium's one of the exceptions. So calcium makes sulfide soluble, so we would say that is aqueous. And I'm looking at the solubility guidelines table. And then we see aluminum nitrate, and nitrates are generally soluble with no important exceptions. So we say, well, that's aqueous as well. And then we get to the right hand side and we see the calcium nitrate, and nitrates are generally soluble with no important exceptions, so that's aqueous as well. And then we see aluminum sulfide, and sulfides are insoluble, and aluminum is not one of the exceptions, so we say that is solid. Okay, and so now we're ready to do the full ionic equation. And how are we going to do that? Well, anything that has aqueous, we're going to break apart into the original ions. And anything that says solid, liquid, or gas, we're going to leave alone. Okay, and so now we see that there's 3 calcium sulfides, so that means we have 3 calcium ions with a 2+ charge. Remember, the charges of these elements follow patterns on the periodic table, +1, +2, +3, -3, -2, -1. And then we're going to say we have 3 sulfurs at 2-. And then we go over to the aluminum nitrate, and we see there's 2 aluminums, and aluminum has a 3+ charge. And then we have 2 times the 3 in parentheses. Keep that in mind. It's 3 in the parentheses means we have 3 nitrates. That means we have 6 nitrates on our left-hand side. The 2 and the 3. 2 times 3 gives me 6. And so now moving over to the right-hand side, we see we have 3 calciums, again, as 2+, and we have 3 times 2, again, for our nitrates, which gives me 6 nitrates. Now remember, when you're doing these things, everything has charges. And then once again, making note of the fact that we have solid over here, we leave the precipitate alone. So it's Al subscript 2, S subscript 3, and it's solid as well. And everything on the full ionic at this point is aqueous all the way across, and everybody has a charge. All right, now we do the net ionic and the spectators. And how do we find the net ionic and the spectators? Well, the spectators are the same on both sides. And so if it becomes part of something, then it's not a spectator, it's actually a participant. So we look and we see calcium is the same on both sides. And so calcium is a spectator. We see sulfide becomes part of the aluminum sulfide on the right-hand side. So that's not a spectator. That's going to be part of our net ionic. And then we see the aluminum is part of the aluminum sulfide on the right-hand side, so it's not a spectator either. And then finally, we see the 6 nitrates become 6 nitrates on the other side. So what's our spectators? So our spectators are the NO3- and the calcium 2+. Those are our spectators because they're the same on both sides. Okay, and so now we can take whatever's left over, and those are what end up in our net ionic equation. There they are. And so we say the net ionic equation is the 3 sulfides plus the 2 aluminums, 3 pluses, ends up in aluminum sulfide. And of course, that's solid. And these guys over here are aqueous. They're still aqueous even as ions. And there they go. So this is a key skill for this chapter. It's a key skill. 1, let me just write them out. These are things that you have to be able to do. 1, you have to be able to predict the product with correct charge balance. In other words, it's this piece right here, this very last piece here. That's what that skill is, number 1. And number 2, you have to be able to balance the equation. There's a lot to this. And 3, you have to be able to determine the states. In other words, solid, liquid, or gas. And then you have to be able to do full ionic equation, net ionic, and find the spectators. So there's a lot to this. There's a lot to this problem. I mean, we're starting out with just mixing 2 things together, and we have to do several steps. We have to predict the products. We have to be able to get the right charge balance like it's done in the blue box. And then we have to find the states. What kind of precipitate did we produce? Or did we produce liquid water or whatever? And so it goes down, it goes down in that order that you have to do. All right. So let me go ahead and do one more kind of reaction that we can have, and that's where we have an acid base neutralization. Acid base neutralization. Okay, now first off, how do you know you have an acid? It has an H in front. And the H produces H plus. That's what makes an acid an acid. And a base is something that produces OH minus. This is OH minus on here. So that's how you can tell if you have an acid. It's going to have an H in the front. And you can tell that it's a base. It has an OH in the back. Okay? And all acid-base neutralizations produce water plus the salt. All acid-base neutralizations produce water and the salt. Now, we have to be able to balance this. And here's the thing. All right, this is the molecular equation. And here is the key to doing acid-base neutralization reactions. You have to realize that the net, we're going to jump straight over to the net before we do full ionic. The net ionic reaction for any acid-base reaction is H plus OH minus gives you molecular water. This is for all acid-base reactions. Okay, and that is going to be what we're going to use to help us balance the acid-base reaction. Of course, these are all soluble. HCl, acids and bases are generally soluble. And of course, this is a soluble salt. So we're going to take advantage of that. So we look up here, and what it means is that with the net ionic equation, if you have one hydrogen, one H plus, you need one OH minus, and you're going to get one water. If you have two, then you're going to get 2 and 2 and 2. And if you have 3, you're going to have 3 and 3 and 3, and so forth. And so we look at the balanced equation, and this is balanced, but really what we should focus on is how many hydrogens do you have, how many OHs do you have, and how many waters do you have? That's where your focus should be, on balancing an acid-base neutralization reaction. And I see that I have 1 and 1 and 1, and I can see that the acid-base portion is balanced. And then if you do that, then you automatically have the right number of the salt ions. And sure enough, you do. So this reaction is balanced. So now we can go ahead and do our full ionic. Now, you don't break up. Don't break up the water. Okay, don't break that up. The only things you're going to break are the things that are aqueous. So if it's solid, liquid, or gas, you don't break it up. And so, but everything else is aqueous. And so acids produce H plus the other piece that it's attached to. So that's H plus Cl minus. And bases produce OH minus plus whatever it's attached to. Okay, did y'all see what I did there? You know, I mean, I'm just breaking it apart. But keep in mind, don't break up the OH. Don't break it up. It's a polyatomic. And then this is going to go to, of course, the liquid water. We'll go ahead and make that liquid. Everything else is understood to be aqueous. And our soluble salt, which is sodium plus Cl minus. And what's the spectators? Well, the spectators is everything other than the H plus and OH minus and water. So let's go ahead and circle in green the spectators. That would be these guys over here. So our net is going to be 1 OH, 1 H plus going to 1 water. That's going to be our net ionic. And like I said, all acid bases are going to have the same net ionic. It'll be 1 to 1 to 1, or 2 to 2 to 2, or 3 to 3 to 3. It'll be one of those. And so our spectators are the ones in green. And that would be the sodium ion and the chloride ion. Those are our spectators. So let me show you another example of an acid-base neutralization where we don't have 1-to-1-to-1. And to show you how it works, let's say that we had, let's say we had phosphoric acid. This is phosphoric acid. Of course, it's aqueous. Acids and bases are generally soluble. And let's say that we're reacting this with sodium hydroxide again, which is aqueous. Okay, and I know I'm going to get water plus the salt, but this is how you do it. What you do is you go ahead and get the same number of OH with H plus. Now we have 3 hydrogens here, 3 H pluses, which means I'm going to need 3 OH minuses. Remember what I said about the net reaction is going to tell you how to balance it. And if I need 3 OHs, I'm going to have to put a 3 over here to balance out the 3 H pluses. We're not even thinking about the sodium and the phosphate for the moment. And then that would give us 3 waters. Remember what I said, 3 to 3 to 3. And so we have 3 waters up here. And we get the salt. And what's the salt? Well, the salt is those 3 sodiums with the phosphate. And I know that's right for the sodium phosphate because we started out with sodium plus and the phosphate ion. This is another reason why it's important to memorize your polyatomics. And then if you cross the charges, the 3 comes down on the sodium and you have the phosphate. So I know that's charge balance. And so now the top equation is balanced. It's the beauty of using the H plus 3 OH minus to give you the 3 waters, is it automatically is balanced. But you should always check yourself anyway, and it is. And so this is the molecular equation, the ME. And now we can go ahead, after we put down the states here, sodium phosphate is soluble salt, according to the solubility table. And so now we can go to the full ionic. And keeping in mind, what do acids do? They produce H plus, and this is called polyprotic because it's producing 3 protons, plus that phosphate. Got to remember our charges on our polyatomics. Phosphate has a 3 minus, plus that's 3 sodiums, plus the 3 hydroxides. Don't break up the OH. It's just 3 of them, and it has a -1 charge. And then, of course, since the water's liquid, we leave it alone. Remember, liquids, solids, liquids, and gases, you don't break apart. And so we have the 3 sodiums on our soluble sodium phosphate, soluble salt. And, of course, the phosphate is still 3 minus. And we can go ahead and write out our net ionic, easy peasy, because it's 3 hydrogens from the H3PO4 plus the 3 hydroxides from the 3 sodium hydroxides, which gives us the 3 waters. And of course, everything else is a spectator. So what's our spectator ions? It would be these guys right here, the phosphates and the sodiums are our spectator ions. Okay, so that's how you do that. It's an essential skill. This is an acid-base neutralization, and the real key on acid-base neutralizations is realizing that for every H plus you need an OH minus, and you get a water. And the products of all acid-base neutralization reactions are water plus its salt. All right, so let's go ahead and do a calculation today where we have a precipitate, where we know we have a precipitate. So let's just start with a balanced equation. Let's say we had aluminum nitrate react with sodium hydroxide to make aluminum hydroxide, which is, by the way, insoluble according to our solubility rules. And let's make 3 sodium nitrates. Okay. And of course, we go through and we check and we see that nitrates are generally soluble, which is aqueous. And so are hydroxides are insoluble, but with sodium, which is an alkali metal, it becomes soluble. Aluminum hydroxide is not soluble. And anything with nitrate is going to be soluble. So we have aqueous up here. And so what we're going to do with this balanced equation is we're going to answer this problem right here. So we can go ahead and write out a problem similar to what we did in chapter 3. Okay, but what we're going to do with this problem, though, is we're going to use something called molarity. Okay, and so molarity is moles per liter. Okay, and so let's say that we have 10.0 milliliters of 0.151 molarity, big M, and I mix with excess sodium hydroxide. And I want to know how many grams of aluminum hydroxide will I get? Okay, now, the first thing that you have to do anytime that you see molarity in any problem, you're given the concentration, which is in moles per liter, and that was milliliters, by the way, of aluminum nitrate. Anytime you have a molarity, the first thing you're going to do is you're going to write it out as a conversion factor. Okay, anytime you see molarity, it's moles per liter, which is a way of going from liters to moles and moles to liters. And what you're going to do is you're going to write it out. This is essential skill is we're going to say, change my color here, that we have 0.151 mole aluminum nitrate for every liter of aluminum nitrate solution. Okay. All right, so that's really the big thing about this chapter is working with molarity when we're doing these calculations. And molarity is moles per liter. And so if you have that molarity, then the first thing you do is you write it out as a conversion factor. And so we do everything else, we do exactly the same way that we did in chapter 3. Anywhere where you see grams, you need the molar mass. Anywhere where you see something going to something, you need the mole ratio between the two, and that comes from the balanced equation. So let's go ahead and get the mole ratio, and that would be between the aluminum nitrate and the aluminum hydroxide. Now, when we say excess sodium hydroxide, we ignore anything that has excess. We just ignore for the problem, because that just means we have more than enough and we don't care. Because remember, we did limit and reactant problems, and if one's limit, then the other one's excess. So we're just assuming that the aluminum nitrate is the one that is limiting. So this is not an limit and reactant problem. And so what do we see here? I see 1 mole aluminum nitrate for every 1 mole aluminum hydroxide. Okay, I see 1 mole each. And so, but even if they're 1 to 1, you still have to use your mole ratio because you're going to have the units cancel. Okay, and so I'm going to go ahead and get the molar mass of aluminum. So I'm going to say 27 plus 3 times 17, because 17 is what OH is, 16 plus 1, and it has a molar mass of 78.0 grams of aluminum hydroxide for every mole aluminum hydroxide. And you see that, other than having to pull down the molarity and write it down as moles over liters, we've done exactly the same thing that we were doing in chapter 3. The exact same thing. Anywhere you see grams, you need the molar mass. If you don't see grams, you don't need the molar mass. Anywhere you go on one thing to another thing, you need the mole ratio between the two, and then you pull that off the balanced equation. And then if you see molarity anywhere, just go ahead and write it down as 0.15 moles, the moles over liters. Okay, so now we're ready. We pull down everything that we need, and now we can go ahead and do our setup. And we draw a really long line, and we start with our measured number. What is our measured number? And so we go back up here, and our measured number is 10 milliliters. And it's the 10 milliliters is what you measured out. Now, the one thing that I hadn't mentioned, though, is that you need to convert your milliliters to liters. And so this is 0.0100 milliliters. Keep in mind, there's 1,000 milliliters for every liter. Okay, so I went ahead and did that. I went ahead and took my 10 milliliters, and I'm going to go ahead and write it down as 0.0100 liters. And that's liters of the aluminum nitrate solution. Okay, now it comes question of just matching. You just need to match. And what do we need to match up with? Well, we need the liters of aluminum nitrate. Where do we see liters of aluminum nitrate? I see it right over here. There it is. And so that's what's going to end up over here. And so we say 0.151 mole aluminum nitrate for every liter aluminum nitrate solution. Okay, and so now liters aluminum nitrate cancels. And of course, just like we did in chapter 3, you put a check mark over it so you don't reuse it. So now what do I need? I need what has moles aluminum nitrate in it. And the only place that has moles aluminum nitrate is right here. And so that's what's going to go up next, the mole ratio between the two. And so I'm going to go ahead and put that down in here. And we say, now I need aluminum nitrate on the bottom though, because the moles aluminum nitrate needs to cancel with the moles aluminum nitrate. So I'm going to flip this over. And so that becomes one mole aluminum hydroxide for every 1 mole aluminum nitrate. Okay, and we're going to take this line out a little bit further. And then finally, putting a check mark over that, we end up with the moles aluminum hydroxide, which is right here, and that's on the bottom, so we need that molar mass of our product, 78.0 grams aluminum hydroxide for every mole aluminum hydroxide. And we're done. All we have to do now is make sure that units cancel, and they do. Moles aluminum nitrate cancels with moles aluminum nitrate, and the moles aluminum hydroxide cancels with the moles aluminum hydroxide, and we have used up all of our conversion factors. Now all that's left is to put it in our calculator, and then we're done. So this whole problem here is a example of one of our key skills that we need to be able to do, times 78, and I get 0.118. I get 0.118 grams. 118 grams of aluminum hydroxide as a precipitate. And matter of fact, we're going to do a lab where we do this very thing, and we're going to be producing from a sodium compound, we're going to producing a calcium compound, and we have to calculate how much we get. So these are two major skills. There's a third major skill, and we're going to do that next time, which is doing these calculations with acid base neutralization. This is a calculation where we have so many milliliters of some solution, and we're going to determine what we're going to get as far as the product goes. So there's several skills, but they all end up looking remarkably similar in the sense of what do you have to do, what do you have to find. Like for instance, this problem we just did, the only key addition is the ideal molarity, which is moles per liter, and so I had to pull down the concentration and make it a conversion factor, and then everything else is just like we did in the previous chapter. And so that's how we end up setting this up.